Catalysts are very important. They're responsible for most of the materials and chemicals that we produce in the United States, in the world.
Catalysis is the idea that chemical reactions are happening, but we have an agent that can actually help the reaction happen more quickly as well as more selectively.
They're very important for reducing emissions into the environment. So the catalytic converter is a huge success.
There's many catalysts in your body, biological catalysts. There's many homogeneous catalysts that reactions that are carried out in solutions of various kinds, and there's many heterogeneous catalysts where there's a reaction between the environment, which is the gas phase, with the solid surface of the catalyst.
Anything that is in our world, 95% of those items have some point in their lifetime passed over a catalyst.
Probably the biggest impact that it's had to humans is the development in the early 1900s of the ammonia synthesis catalyst. So that allows us to fix nitrogen from the air, and we need fixed nitrogen to make fertilizer. If you had a room full of people, 40% of them wouldn't be there if it weren't for the ammonia synthesis catalyst. So that's a pretty big impact.
Catalysis has always been a core discipline. It will always remain a core discipline as long as we want to do any sort of chemical conversions. This is how you get greener processes. This is how you get more cost-effective processes. This is how you can implement totally new reactions. It all comes from catalysis.
Catalysis, broadly speaking, really strongly influences all the ways we think of the future of energy. And so energy and catalysis are very tightly coupled.
The question is, can we develop catalysts to do new chemistry that we presently can't do?
Rather than taking light hydrocarbons coming out of, say, the petroleum stream and cracking those for all of the materials that we use for engineering plastics, polyethylene, polypropylene, things like that, we now take very pure ethane, crack that, get ethylene, which is fantastic if you want to make polyethylene. It's a problem if you want to make all of the other bits. I mean, if you imagine all of a sudden somebody invents a pig that only makes ham, where are you going to get your bacon from? We kind of have that problem in chemical engineering where you can very efficiently make ethylene, but people are needing to learn how to make propylene. People are learning how to make C4s on demand, even some aromatics, just things that used to naturally come along for the ride that we've built a huge chemical infrastructure around. We have to come up with new ways of making as we shift from petroleum to natural gas.
The Catalysis Center goes back to the 1950s at Northwestern, and a couple of people, Vladimir Apatiev and Herman Pines. And so they're very important people in the history of catalysis worldwide.
He took very seriously his appointment, and he had students, and he set up a lab here, and that was really, at least in my mind, the beginnings of catalysis at Northwestern.
Britain also had an air force. An air force outnumbered 10-1 by the enemy, both in men and machines.
They developed a very active program at UOP, which led to many major discoveries at the time, one of which was the discovery of how to improve the octane rating of a fuel for airplanes, which was then quickly put into a process by various companies, and the fuel for the planes produced shipped to Britain and was instrumental for the British in terms of fighting off the German airplanes at the time. And so the English then were competitive and could keep the German Luftwaffe at bay.
There was an environment there that allowed that work to happen. And that's what we tried to create within a university.
And then in about 1970, the university officially sets up the Center for Catalysis and Surface Science and joins these two fields.
They link people together in ways that allow folks to look at a common problem from multiple points of view. And that's what interdisciplinarity is about.
So it requires experts in synthesizing materials, understanding reactions, characterizing materials, doing modeling to understand reactions at the mechanistic level.
Way a material scientist would think about the problem and approach the problem could be quite different than the chemist and the physicist and the chemical engineer. Engineering always is superimposed in a very important way.
And we can all do that under one roof here at Northwestern. Graduate students that come in to do work in my research laboratory can be trained by somebody down the hall in spectroscopy, or can go down the road, metaphorically speaking, to Argonne National Lab to pick up all of the pieces of modern catalysis science, and that's very hard to do in many places.
The CleanCat core facility, it's a user facility that's dedicated to heterogeneous catalysis research. So it allows users from different research groups who may not specialize in catalysis. It offers them the opportunity to learn our field, learn different techniques in our field, and it offers them the opportunity to use instrumentation in our field. It really serves as a hub for the interdisciplinary nature of the Catalysis Center because it serves as a centralized facility that students from different backgrounds can come together and learn the field and learn these techniques that are really important for doing research in this field.
And that brings together people who are looking at the same issue, but they're looking at it with a lens that's different from each other, and therefore you end up in conversations about an issue that you think you understand deeply until you hear it from the point of view of somebody else. And then you start thinking, well, you know, either I didn't understand it, or that brings a whole new way of solving the problem, of approaching the problem, or understanding the problem that is really interesting to the faculty, to the graduate students, to the postdocs, to the staff.
So one of the collaborations that Northwestern University has is with Argonne National Labs and the Department of Energy with something that's called the Joint Center for Energy Storage Research, or JCESR. What we are doing is working on the materials that might replace lithium. So the project is really on multivalent cations that could possibly replace lithium. And so we always think of what's the technology beyond lithium-ion technology. So lithium's in group 1, and it carries a charge of just 1 unit of positive charge. So again, a battery, the next generation of batteries perhaps will be based on this element, magnesium. The material that we're studying at the present time then is made from sulfur, chromium, and again then magnesium.
There's still an emphasis on understanding how catalysts work, but I would say what really distinguishes us from most other places in the United States is our focus on making new things.
These are hard problems, and advances in characterization have gotten good enough now that, as I said before, the structures that I've postulated or been able to discuss indirectly, we can now observe directly.
If we make a really spectacular catalyst, then everybody will benefit.
This is a very exciting opportunity, I think, for the whole university to broadly understand the needs that clearly are going to impact the quality of life of not just people in the United States, but everyone around the world.